All right. Seems we are fine finally. Uh, we are not fine. That's the right one. Okay. Right. Hope finally it's okay. So let me start thanking the organizer for inviting me, which is very nice of you, Jose Manuel. Yes, but it doesn't work. Oh, now it works. Right, everything works. Nice. Okay, I'm afraid this at the last night was pretty disastrous for well for our audience and for me for myself too. But let's try to do our best. Before I start, I would like to share with you a news that I learned today morning. There is a new organization which is called International Society for Quantum Gravity, and the web address is isqg.org. There are some friends of ours who actually are members of it. I believe, Jose Manuel, that Daniele Oriti, who is the chair of this organization, is our member. So everybody is encouraged to go to this webpage and register there, because there are going to be some activities there which might be pretty interesting. Okay, well, what I would like to spend this 4 hours and additional tutorial will be doubly special relativity and relative locality. And I'm uncertain if I have too few slides or too many slides. We'll see it. If there are too few slides, then we can spend some time discussing things. And I encourage everybody to ask questions if something is unclear. Okay, so let me start. So there will be 2 parts. Today I will talk about doubly special relativity and the kind of modern understanding what doubly special relativity is. And tomorrow I will talk about relative locality. And hopefully tomorrow also during tutorials, I will just do a couple of calculations that I think are interesting. And which are going to be omitted in this lectures. It's time for me to advertise.
Just stop.
Oh, sorry. Okay, now it should work. Okay, good. It's time for me to advertise the book that we wrote with Michele Arzano, who's gonna be here. Tomorrow, and with the help of Andrea, with Andrea Bevilacqua, who is here, we will try to write some lecture notes following exactly these two lectures. So, part 1, doubly special relativity. Okay. All right. So let me tell you first what the idea. What's the rough idea? The idea is the following. Well, first of all, doubly special relativity is supposed to be kind of a limit of quantum gravity, some particular limit of quantum gravity. So let me start, or particular regime. Perhaps it would be better to say a particular regime of quantum gravity. So let me first tell you briefly what quantum gravity is. Well, you know a lot about quantum gravity from lectures of Renate last week. But roughly speaking, when I try to find a definition, what does it mean that I have to do with quantum gravitational phenomenon, then basically from dimensional analysis, quantum gravitational phenomenon or quantum gravity effect is an effect in which a physical system has a characteristic size of order of Planck mass, and at the same time, it has characteristic energy of order of Planck energy. Right? This is basic. This is the basic intuition. So suppose I have a scattering of two Planck energy particles, which are pretty far away. So the energy scale is Planck scale, but the length scale, the distance scale is pretty large. Then the effect is not quantum gravitational. They just exchange gravitons. And this is this basic intuition that in order to have a really quantum gravitational effect, not only I need a quantum energy, so particles with energy of order of Planck energy, but also the impact parameter of the scattering, say, should be of order of Planck length. And indeed, there are many people actually trying to analyze this Planck energy scattering, and indeed it turns out that when the impact parameter of the scattering goes down to the Planck scale, something starts happening, something weird starts happening. We don't completely understand it, but there is plenty of papers about it, and again, and in this lecture notes that we're going to prepare, I will give you a list, or some list of references for your further studies if you're interested. Okay. So let me tell you what's the basic idea. The basic idea is that let me start with what's happening in some limits. Well, if the energy scale characteristic to the process is much smaller than the Planck scale, my Planck energy scale, which I call kappa here, and the characteristic length scales is much larger than the Planck length, then we know that the world is described by special relativity and quantum field theory, or general relativity, if you wish. But assume that the space is flat. There are not really very massive bodies in the game. So this is you may say that this is the weak gravity regime of quantum gravity. I'm afraid probably this red part is not really very easy to read, isn't it? Well, I'm sorry, I should have changed. So I will change colors tomorrow. So okay, so I will read it for you. On the other hand, you can contemplate a possible the possibility of the regime in which the energy is of order of Planck energy, and at the same time the characteristic distance is much larger than the Planck distance. You may say that you have to do with Planckian scattering, in which you neglect the effects of quantum of space-time form. You know, the form structure of space-time are completely negligible because of this, because this fluctuation of space-time itself are relevant at the landscape of a Planck length. So since the system is much larger than that, the system just doesn't feel these fluctuations. And this regime is called the relative locality regime for the reasons that it will become. Well, this is really the historical reason why it's called this way, because it was really spelled out in this form when the relative locality first appeared. And this is the regime. This is basically the regime we are going to be interested in. So the regime, in this regime, what we have to do with a relativistic theory which possesses a scale of mass. And then immediately a problem arises. The problem is the following. And this was the problem that Giovanni Amelino Camellia, who is a founder of this whole business, asked himself in 1999. So his problem was the following: if I have a scale of mass, or a scale of length equivalently, then, and if I want to have all the relativistic symmetry to be preserved, then then we know that the mass as measured by different observers in special relativity is different. I mean, the mass as say kinetic energy defined as a kinetic energy of the particle. Well, so the question is, if I have a scale of mass and I assume all the relativistic symmetries, then the question arises, which observer actually measures this mass, right? Because the different observer, if different observer moving boosted with respect to one another, actually try to measure a mass of the particle, inertial mass of the particle, just by measuring how this particle is getting, the trajectory of the particle is getting curved by external field, they found that the mass, of course, depends on velocity. So the question is, what is this? On the one hand, we want to have a universal scale of mass, but on the other hand, we really need to say what is the observer that measured this mass? Or perhaps, is it possible to formulate a theory which possesses the mass scale and preserves all the relativistic symmetries? Well, of course, a simple way out is to say, well, there is a special observer who measured this mass, and then, well, the symmetry between observers is actually, this is a privileged observer, so the symmetry between observers is actually broken, and then we have to do with something which is called Lorentz invariance violation. But the idea of doubly special relativity is that we specifically don't want to do that. We don't want to break symmetries. We want to have a relativistic theory which possesses the same set of symmetries as standard special relativity, and at the same time, it actually possesses a scale. And today, I will spend my time describing how this can be done. So let me give you some kind of a historical way of development, historically, Galileo was the first who formulated a relativistic principle, which is essentially telling you that the laws of physics take the same form in all inertial frames. These laws are the same for all inertial observers. And in this theory, so in classical Newtonian mechanics, there is no specific scale of velocity. And immediately, given that there is no scale of velocity, you immediately see that the only composition rule of velocity is a linear composition rule. You cannot go beyond the linear composition rule of velocities, because if you want to make it nonlinear, you really need the scale, just for dimensional reasons. So if I would like to have V1 plus V2, and I would like to add some terms which will be trilinear, say V1, V2, V1, something of this sort, with some, I don't know, say something like this, right? Something of this sort. You can think about it, but for dimensional reasons, this term has dimension velocity cubed, so you really need the scale to make dimension of this one. Well, I can think about simpler thing, right? Well, no, because it's going to be a vector. So this is the simplest thing you can think of. Probably it should be something like, I don't know, whatever. So you have some trilinear. You need to make some trilinear to make this guy into trilinear vector, which is possible. But then the argument goes that since this object is trilinear in velocities and this one is linear in velocity, you need the scale of velocity in order to make it work, right? The formula to make sense. And I will give you an explicit example of additional velocities later on. The point of this exercise is that if you want to go beyond linear theory, you really need to have a scale, and this is going to be an essential argument in all what I'm going to say today. Then, in 1905, which is more than 100 years ago already, comes Einstein, and he said, well, there is a scale of velocity, which is c. And if you think about three velocities, so, and this is a scale, it's a fundamental scale, it's observer independent in the sense that all observers measure the same velocity of c, right? This was kind of an experimental input made into fundamental principle. And what Einstein did, Einstein wanted to preserve the relativity principle, at the same time adding the scale of c. And then you can do it, you know it. It has a particularly elegant formulation in 4 dimensions. So there is a particularly elegant formulation in 4 dimensions of special relativity. But then, of course, you can think of a rule of additional velocities, of 3 velocities in special relativity, and you get a formula which is extremely complicated, and which is, of course, experimentally testable. And as I said, I will return to this at some point. DSR, so the idea of DSR is actually to extend this by adding the additional one more mass scale, one more scale, which is a scale of mass, and at the same time preserving the relativity principle. So that's basically the idea. And since we already know about an important scale of mass in physics, which is the Planck scale, and we know that the Planck scale has to do something with quantum gravity, the hope is that DSR has something to do with gravity, quantum gravity, really. So there are some effects of quantum gravity which can be captured by this theory, and the hope is that this effect of quantum gravity might be actually testable, experimentally. So there is a kind of a phenomenology. The DSR models, it's called, doubly special relativity. It's also called by many deformed special relativity. And although I prefer the name doubly because when Giovanni started, he used this name, Doubly Special Relativity. So I get accustomed to, but probably the term deformed special relativity probably reflects better what's really going on. You're deforming things, and you're deforming things in some particular way, and also I'm going to tell you about this. So anyway, I will use the term exchangingly doubly special relativity and deformed. So in the case of deformed models, may describe doubly special relativity, may describe some deviation from special relativity. And these deviations, which could be thought of as being of quantum gravity origin, they could be actually tested. And one of the way of testing this is to test if the photons coming from distant sources of different energies actually have different speed. And in the course of these lectures, I will actually compute the speeds in several models. And I will show you that some of the models actually predicted or predict the energy-dependent speed of light, and some don't. So this is, and this thing, at least for some class of deformation, some class of dependence of velocity of energy can be already tested, and actually has been tested, are being tested all the time. And this cost action is about this. So this is the most popular fundamental phenomenology of application, phenomenological application of quantum gravity model. That's being considered. Not the only one, but the most important one. All right. So, okay. So let me tell you one more thing. A simplest model, physical model, which carries or has whose structure is actually dictated by the symmetry principle, is a model of relativistic particle. And in the case of this phenomenological application, this is actually the model that we're interested in, because that's the model that describes just non-interacting particles, which is exactly what we want here, because you can think of the photons emitted here as non-interacting particles moving for billions of years before being detected on Earth. So let us now start this theoretical part, considering just the simplest relativistic model of particle. I believe that most of you already saw this action. This is the action of relativistic particle. The thing which is important here, and which is probably not the most common way of writing this action, is that I use the first order action instead of second order one. Usually when you talk about the particle, use the action that is quadratic in velocities. But equally well, you can actually use the action which is linear in velocities and involves momenta as an independent variable. So this is the action of a relativistic particle. This is the kinetic term, which is essentially the simplest possible, right? You have velocity multiplied by momenta. There is relativistic constraint coming from the representation theory of Lorentz group, which essentially is telling you that p squared, that the standard dispersion relation or mass shell condition of relativistic particle of relativistic theory is satisfied. The particle has some mass m. And I'm using, I didn't write it here, but I'm using the signature minus and pluses. All right. N is a Lagrange multiplier. As you see, it's just a multiplier, and the equation of motion of N is a dynamical variable, which essentially imposes the mass shell condition. So let me look at the equations of motion. Well, this is very simple. The action is particularly simple, so it's simple. It's easy to find out what are the equations of motion. If I take a variation over x and integrate by part, so I move the dot here, right? Because in the standard way of doing the variation calculus is that you do need to remove all the derivatives from the variation. Okay, so you take a variation of x, you integrate by part, and you get this equation, right? Is it clear to everybody, or should I spend a moment just to show it? Tell me, is it clear? Good. Then the momentum equation is just algebraic. It tells you that x dot is related to p and n. And then the n equation is actually just a mass shell. It's just a mass shell condition. Okay? It's clear? Now, there is kind of a trick in it, because, and I'm not going to dwell much on this point. The trick is that n is a kind of a gauge variable here, and you can always fix it after calculating the equation of motion. You can fix the value of n. Essentially, n is related to the definition of tau, the time along the trajectory, or in fact the parameter that numbers the points on the trajectory of the particle, which is of course arbitrary. So n reflects this arbitrariness. And for those of you who know, it is the one-dimensional. It also can be thought of as a one-dimensional gravity models of gravity in one dimension, and then n plays a role of a tetrad of gravity. One way or another, there is a gauge freedom, which lets me fix the gauge of n after we computed the equation of motion, and the natural value is 1/2m, so that we obtain a standard relation between force velocity and force momentum. Okay, as simple as that. Please ask me questions if something is not clear at this level, because then we're going to jump to the more complicated models, and I will repeat calculate these arguments. So it would be nice if it would be good that everything is clear here for you. All right. What's important for us is the speed of light. So let me calculate the speed of light. Well, that's actually pretty trivial, because I know that x dot is proportional to p dot. Then in the case of massless particles, the mass shell condition tells you that p squared is equal to 0. So x dot squared is equal to 0, which means that the particle moves on the cone, which means that the velocity of light is the velocity of particle is just velocity of light. But you can do another calculation. You can say that v squared is dx over dx0. x0 is just a time squared, which is equal to x dot over x dot 0. Okay. Squared, which is p over p0, when the p squared over p0 squared, actually, when the condition that the p squared is equal to 0, and you can easily see that this is just 1. Okay, so indeed, the relativistic particle, that this Lagrangian reproduce all the properties of relativistic particles we can think of. It's a good model. So let us now try to find out what are the symmetries of the action. Again, it's gonna be important for us later on. Well, certainly the action has the space. Well, n is invariant under all relativistic symmetries. Is a kind of a scalar. So I don't even bother to write what the transformation of n are. All right. So let's list all the symmetries. Okay. Well, first of all, there is a obvious translational symmetry with respect to the rigid translation. So epsilon is just a constant. It's physically, of course, understandable. I can move the trajectory, in space-time without changing its physical properties, right? So that's just translation symmetry. And indeed, it's manifest here because epsilon dot is actually 0, right? P doesn't change, so this guy doesn't change, this doesn't change. So the change of this term is 0, epsilon dot, which is 0, so delta S is 0. All right, then there is again an obvious rotational symmetry, which actually moves, just rotates x in piece. And of course, and it doesn't change the zero component of x and zero component of p, so it doesn't change time and energy as usual. That's what rotations do. They rotate space vectors. And they rotate space vectors. This is the infinitesimal transformation with the parameter rho. This is the parameter of infinitesimal translation. This is parameter of infinitesimal rotation. And you can actually convince yourself easily that both this term, so this term is changes under, can potentially change under rotation because p is changing, but this term and this term are actually invariant. You can check it explicitly just using this explicit form of the transformations. There is no mystery about it. This is exactly what we expect because I can rotate the trajectory of the particle, or I can rotate an observer. So I might rotate myself, or I may rotate the trajectory. Oh, by the way, this is something that I should mention. That's not going to be relevant here, but I would like to stress it because it's important. There are two kinds of transformations. There are passive ones and active ones, which are actually, in most theories they're identical, but sometimes they are not. The passive transformation is the transformation of changing the observers. I have the same process, and I have several observers that observe it. They might be translated with respect to those observers, might be translated with respect to one another, or rotated, or Lorentz boosted. And these are the passive transformations. And there are also active transformations in which I have one observer, but I transform the system. I rotate the system, or I boost the system. So for example, I have a particle at rest, and I change it to the particle moving with some velocity. If it's massive, of course, because I cannot do it with or I can rotate the system, right? These are the active transformations. In general, well, in most cases, there are no difference. But in some cases, it's kind of tricky, especially in the case of Lorentz invariance violation. If you're actually interested in Lorentz invariance violation theory, this subtle difference actually starts playing a role. All right. So the last one are Lorentz transformations, which change both the energy which relate energy and moment and linear momentum, and which relate the space position with time. And again, you can explicitly check that this transformation that are infinitesimal transformations, so lambda is an infinitesimal parameter, so you really need to check it only up to the leading order in lambda. This transformation actually don't change the action, and I believe that you're also familiar with this one, right? So I don't really need to show you explicitly. These are the Lorentz transformation. The proper Lorentz transformation, the boosts. Well, proper Lorentz transformation is something different. So just the boost. So how many symmetries do we have? We have 4 translations in 4 dimensions. We have 3 rotations, and we have 3 boosts. So there are 10 independent parameters, and the algebra of symmetries is a 10-dimensional algebra, or the group of symmetries is a 10-dimensional group with parameters. I call these parameters lambda, rho, and epsilon. Okay, so let me do it a little bit more abstractly. So if I have a translation acting on something, I may say that this is the action of momentum generator or translation generator. Let me call it P mu. multiplied by this infinitesimal parameter epsilon mu acting on something. This triangle, rotated triangle, actually denotes the action. So if I want to know what delta t acting on something is, then I need to take epsilon, some generator, some operator, which acts on this something, right? So this is the definition. Then I have rotations acting in the same way, and so on. And as an example, I know what these guys are, right? So P mu acting on X nu is delta mu nu, so that epsilon mu nu P mu. Okay, so let me write it down because I didn't write it here. So delta T of X mu is equal to epsilon, well, epsilon rho times P rho acting on X mu, which by this equation here is equal epsilon rho times delta rho mu, which is epsilon mu. Okay? So I separated an infinitesimal transformation into the parameter of transformation and the generator. The generator captures all the information about the transformation. And again, we know the transformation should form the group for physical reasons. You can think of it. The statement is pretty obvious if you think a moment that the transformations should, finite transformation should form a group if they are physical. Well, because it should make sense to take one transformation after another. So if something is a symmetry, then it should change the system. So the composition of those two symmetries doesn't change the system either, and so on and so on. There is a unit transformation, there is an inverse transformation. And which means that infinitesimal generators should form a Lilo algebra. And you can compute, just by using this, you can compute the commutator. Just you really need to compose two transformations and then take the inverse and play it a little bit one way or another. I'm not going to, because we are not studying algebra. This is the algebra of symmetries, and it's called the Poincaré algebra. So what's our essential point? The translations commute. The rotation acting on spatial translation actually rotates the spatial translation. The rotation doesn't act on the time translation. The boosts act the same way. The rotation composed to rotation. The boost generator is a vector with respect to rotation, so it actually essentially behaves like P. And two boosts. This is the tricky part. The combination of two boosts gives you essentially the rotation. Okay, that's the algebra, and this algebra is called Poincaré algebra. And I believe that you already that you know it. Okay, good. So now we have all tools, and we start. So let me summarize for a second. We have I have the standard relativistic particle, the simple model, special relativity. I found that there is a Poincaré symmetry. And we know the Poincaré algebra, which is relevant also in quantum field theory. I would say it's fundamental to quantum field theory. So now let us try to generalize. The first naive generalization is the one in which you change the dispersion relation somehow. So you say, well, suppose there is some quantum gravity effect that changes the dispersion relation. There are plenty of works about this, especially in 2000, well, around 2005, there were tons of papers because people were considering additional terms in quantum field theory, higher order terms that essentially resulted in the change of dispersion relation. So translated to the particle model, we say, well, why don't we consider the following thing? Why don't we consider the changing or so generalizing this p squared plus m squared into some function of p which will contain the scale kappa plus m squared. Well, we need the scale kappa, as I already told you, because if I want to replace this p squared with something which is higher order, contains higher powers of p, I need some scale of mass or momentum to compensate, right? So that the dimensions are right. Well, so what are the conditions? Well, first of all, this cannot be just a function of p squared because it's going to be trivial. If it was just a function of p squared, you can easily convince yourself this is kind of trivial modification. Nothing really happens there. And the reason is that essentially, you know, the condition p squared, well, especially for example, for the velocities, you will find that photons still move with the velocity of light in a kind of a trivial way. And the only thing to do to go back to special relativity is essentially to rescale, to change the definition of mass, and everything is going to be back just relativistic. And besides, if this function was just a function of p squared, it would be invariant under standard Lorentz transformation, Poincare transformations, right? Because p squared is invariant, so any function of p squared is invariant too. So nothing's going to change, but we specifically want to have Lorentz invariance violation. So this cannot be. This function must be somehow different from just p squared. And the correspondence principle is that if the scale, so if the Planck scale, if the scale of mass if this mass becomes infinity, which means that it's so big that you know that the scale of energy of any process is actually much smaller than the scale, it should give me back p squared. And as I stressed here, it must contain a scale of mass. Sorry, it's red again. But as I said, I'm gonna read all the red marks here. Okay, good. So we assume that in the case of Lorentz invariant violation, we assume that the mass condition is not Lorentz invariant. So that, okay, I know what this generator is, so let me explain. I know that the generator of the boost, do you know that the generator of the boost can be represented in this way, acting on momenta? You can change it, you can actually check it explicitly, but this is what it is. And we assume that this guy, this mass shell condition, this C of K is not Lorentz invariant, which means that if I act with this operator on this modified dispersion relation, I don't get zero, right? In the standard case, this was zero, right? Because if here is p squared, well, perhaps there is a time to show it. So if this guy was minus p0 squared plus p squared, p vector squared, then I will get from here, I will get p0 pi times 2, and from here I will get minus pi p0 times 2, so it would be 0. But if I have more general form here, then it wouldn't be 0, and the Lorentz invariant is violated. The system doesn't, the particle model with p squared replaced by this c kappa is not Lorentz invariance anymore. And then the velocity of light, which I define this way. So this is x dot, and so this is the velocity square of velocities, x dot squared over x dot x0. I substitute the equation of motion, which are simple, and I got that in general, this thing is just not equal 0, not equal 1. And in general, is momentum dependent. So the lesson is here that if we modify the dispersion relation, we find that for photons, the energy is, the speed of photons is energy dependent. We may have an effect, we can see it. There was actually the first paper about astrophysical sources which emit high energy particles, high energy photons, and in which this Lorentz invariance violation scenario can be tested, was published, I think in 98 or 97 by Ellis, Mavromatos, Nanopoulos, and Amelino. And actually, the reflection on this led Giovanni Amelino Camelia to this idea of doubly special relativity. So the idea is, could we actually change this guy without violating the relativistic symmetries? So I don't want the Lorentz invariant violation. I don't want this scenario, although there are people who think that there are good reasons to believe that this is very relativistic, realistic scenario, and we should, and well, certainly we should test it. So instead, let me tell you about deformations. Now I want to deform things. Well, what I want to do, I want to insist on relativistic symmetries. And surprisingly, if I have a deformed dispersion relation, so CK is a non-trivial function of P, it's pretty easy to preserve Lorentz symmetry. There is no real problem with that. So let me tell you how it comes about. Surprisingly, we can make Lorentz invariant basically any deformed dispersion relation. Dispersion relation. I mean, for that matter, I think that even just a standard Galilean dispersion relation can be made Lorentz invariant if you want. How you do that? Well, let me assume that this generalized dispersion relation is manifestly rotational invariant, just for simplicity. The physical reason is that we don't see any deformation of rotational symmetries. I mean, when I rotate, and if I look at the experiment, high energy experiment, we don't really see any deformation in rotation symmetry. So just for simplicity, there is nothing fundamental about it, but just for simplicity, let me assume that this modified dispersion rotation is manifestly rotationally invariant. So it depends only on P squared, which is the spatial momentum squared, which is manifestly rotationally invariant, and energy. Okay, good. So let me try to build a new boost generator. You remember, well, it should be, I'm afraid there is a misprint here. So let me write it on the blackboard. Oh, by the way, okay. So perhaps you see some of you see what is the misprint. If you look at this, formula. Oh well, no. Okay, sorry. No, that's okay. I'm sorry. I also, I was also yesterday on the party. All right. No, everything is okay. So in the case of the standard undeformed boost generator, this function A is just P0, and this function BI are just PI. So it's probably, I should say here, instead of BI times of function of P squared and P0, I should say that this is PI times B. But it's not that relevant. What is relevant is that I assume that if I assume that this commutator of two deformed boosts gives you still a rotation, so the algebra, Lorentz algebra, is not deformed, and at the same time the action of this operator of arbitrary dispersion relation gives you 0, I'm not going to show you this explicitly, but what I'm telling you is that these two conditions, so undeformed Lorentz transformations, so the Lorentz sector of Poincare algebra is not getting deformed, and at the same time, this modified boost do make this new dispersion relation invariant, these conditions can be actually satisfied. So this is pretty technical, so let me tell you what essentially is the point. Essentially the point is that if I have modified this dispersion relation, I can modify the boost accordingly so as to make the dispersion relation Lorentz invariant, at the same time having the Lorentz symmetry satisfying the same algebra or the same group property. So the Lorentz group is not modified. The commutators essentially define the Lorentz group, but the action is modified in such a way that this particular function is actually invariant under Lorentz. And of course, it is invariant manifestly under rotation by definition. So that was easy. And if something comes easy, it's usually not very interesting. Yes. That's a strange representation of the Lorentz algebra itself. But of course, it's a strange representation of the Lorentz algebra itself. The problem is that this is not enough to have a relativistic particle, more deformed relativistic particle possessing all the symmetries, because the relativistic particle has on top of this mixture condition, it also has a kinetic term. So you must make sure that the kinetic term is invariant, and you can easily convince yourself that if you use this representation of the boost generators with canonical kinetic term, the action is not invariant. So you can make the modified dispersion invariant, but if you keep the standard kinetic term, just x dot p, then the action is not invariant anymore. All right. So, and the question is why it's so easy to do that, right? If something goes easy, if something comes easy, it's usually interesting to understand why it is so. Okay, so let us try to understand why it is so. The reason is basically that you can always associate it with this modified. So you can trace this modified action of the boost with the change of coordinates in momentum space. Right? So you replace one momenta by another momenta in a nonlinear way. You can do it because you have the scale. And then what was originally p squared, right, became some non-trivial function of the new momentum variables. Okay? And then, but you know, nothing changed really. So you modify, if you change the variables in the definition of boost generator, nothing gonna change, right? I change variables. This is just a change variables. I change variables in the Marshall condition. So p squared goes to, right? But at the same time, I have a boost generator which was expressed in terms of p. It goes into the boost generator expressed in terms of k variables, right? If this transformation is smooth enough, then of course, if n preserved this guy preserves this. Okay, it's just a change of variable. Okay. All right, but let me give you an example. This is an example that we're going to use in a moment, and of course, it's not that easy for kinetic term. So let me use an example. These are my original kind of Minkowski space momenta. These are the new momenta k that I defined by this kind of a very nonlinear transformation. For historical reason, this is essentially the historical reason why this transformation is so relevant. And I will tell you later. I will tell you about in a moment. So basically, this dispersion relation, which is expressed. This is a kind of again historically the dispersion relation that historically was that is of relevance historically is actually in terms of this p variables is again expressed as a complicated function. Well, indeed complicated function, but of p squared, so it's more, so it's not really mysterious that it's actually invariant. So if I change variables from p to k, then I need to, if I modify the boost generators, expressing them in terms of as differential operators in terms of the, it should be k0, sorry, in terms of k variables, then this guy is going to be invariant on this modified boost because this guy on the right hand side is invariant on the standard boost, right? Is it clear? So the point so far is that I can think about the Lorentz invariant violation, and the Lorentz invariant violation particle model is I stick to the standard kinetic term at the same time modifying the dispersion relation. And indeed, such action is not Lorentz invariant. We have all kinds of effects we can think of, we can measure and stuff. On the other hand, the first idea that the first thing that we actually realized, trying to understand how easy it is to deform boosts so as to make this dispersion relation invariant, is just a change of variables. And this change of variables actually will play an important role later on as a kind of a guiding principle for the construction that I'm going to present you perhaps after the break. Right, okay. Let's take a break, 5-minute break, please. But so okay. I hope that tomorrow we won't start at 10 again. On the other hand, why not? Anyway, so let me speed up a little because I think, contrary to what I thought that I would actually cover everything in 1 hour. I'm already behind the schedule, so let me speed up. All right. So what next? Let me see. Changes of coordinates, right? This is actually a major problem. This is something that I used to quarrel and argue with Giovanni Amelino for 20 years now. And there are two camps. Giovanni is in a camp who thinks that every momentum is actually physically relevant. So if I have a different moment, different momenta, like, of this transformation, so the K is physically different than P. And I think that K is physically completely equivalent to P. And the reason is the following. So let me give you the reason. The reason is the following. The change of coordinates cannot be physical, but I stress that some of the experts don't agree. And the argument is the following. So imagine that a math saboteur hacks into CERN's system and changes computer code. Okay? So that the output now, instead of the components of momenta, will be now some arbitrary functions of them. Okay? So I have a detector, some colorimeter, it measures something, then it goes through the code, and then at the end of the day, you get some P, which is the standard momentum. Right, the standard momentum in terms of special relativity. But assume there is a guy right here who actually hacks the system, and instead of P, I get K. Does it change physics? Well, of course, it cannot change physics. Right? It cannot change because the physics is the same. The scattering of the particles here is just the same as it was. If the map from one momentum to another one is a smooth, nice differentiable, and so it should be perfectly equivalent description of the of physical process. That's why I think that if you really have the only thing you're having is just a change of coordinates in momentum space, as we did in order to make, for example, the dispersion relation, which is nonlinear a priori, we make it Lorentz invariant. This change of coordinates cannot be of any physical relevance, right? The process is the same. It doesn't really matter which momenta we use to describe it. Of course, it's tricky. It's kind of tricky. So it's not completely trivial. Because then, if I'm telling you that is in a sense all the momenta obtained from the original one by coordinate transformation in momentum space are equivalent physically, then the question is, so that's the point I already made. But there is another point actually, which is in red, so I read it. The point is that the question arises, and this is something which is highly non-trivial, because the momenta, all the coordinate system in momenta related by some coordinate transformation in momentum space are equivalent. Then if I measure momentum equal 10 of a photon at CERN, which one is it? I mean, which momentum is I'm measuring? Right? So it's not completely trivial. This statement is, of course, kind of reasonable physically, but then you really need to ask yourself a question, which coordinate system, this 10 measurement, to which momentum, in which coordinate system it actually corresponds to. And the only way out of this is, I believe, something that already was advocated by Einstein in general relativity. Only coordinate independent objects are physically measurable. That's it. All right, so let's continue. This is a deep problem, as I said. This is already what I said. It's again in red, so we cannot read it. So let me continue. Now, I already talked about Einstein, and Einstein in the transition from general relativity, from special relativity to general relativity, he actually said that there is a one-to-one correspondence between gravity and curved moment and curved space-time, and the only objects that can be that are physically measurable with the symmetry with respect to change of coordinates, and the only measurable objects in general relativity are those that are actually invariant in some specific sense with respect to the change of coordinates. Okay, and then 30 years after, about 20 years after general relativity, in late 30s, Max Born actually came with an idea which I think it's extremely important for us. He actually said, well, why don't we assume that the momentum space is curved as well? It's a curved manifold. It's not a flat manifold, it's a curved manifold. And he actually tried to find some consequences of this. Then there was Snyder, about 10 years later. Snyder actually formulated the first curved momentum space physical theory. I will not discuss it, but it's important to remember that it was Max Born who actually first came with the idea of curved momentum space, which is going to be a central idea of what I'm going to tell you now. So what are the conditions that, all right, so in the context of the theory that we are interested in, we're interested in the theory that is relativistic, so it possesses all the symmetries, all the relativistic symmetries, perhaps in some modified sense. And we also need to, and there is kind of a correspondence principle that tells you that when the scale goes to, the mass scale goes to infinity, we should recover the special relativity, right? There are two physical conditions that we need to take to start with. And then, since we have this curved momentum space, then there is a natural explanation. It might provide for us a natural explanation for the scale, and the scale must have some kind of a geometrical meaning. So not only I need the corresponding principle and the deformation, but I also need to get some understanding. So the first thing that you can do, the simplest possibility, is to take a momentum space to be a space of constant curvature, with the curvature being 1 over kappa squared, which is the Sitter space, or submanifold of the Sitter space to be precise. I will tell you more about it in a moment. The Sitter space is basically this manifold. It looks like this. I believe that you have, yes. Yeah. That's not completely clear to me, but if the space is not maximally symmetric, then the curvature is not the changes from point to point. Only for maximally symmetric spaces, the curvature is constant. And since I have a scale which is universal, so this is the simplest model. Of course, you can contemplate the more complicated ones. So, for example, you can contemplate a model in which the scale depends on momenta, right? Which would be going beyond this. But this simple model has very many interesting mathematical physical features. So I will stick to this. But of course, you're right. You can consider more general one, and it's certainly interesting to do that. And I believe, well, if I know, I mean, to my knowledge, nobody really seriously considered a model like this. I mean, there was some hints in the papers of Majid. But apart from that, there are no real application, both mathematically, so both in a, from the mathematical physics perspective, and especially not from phenomenological perspective. But of course, you can contemplate this. It would be very interesting. Okay, so that's the idea. All right, now, so let me go, let me turn back to this transformation that I already showed you. They are special because they are actually pointing to this momentum, the Sitter momentum space. Okay, sorry, actually, I went, okay, so this is again this transformation that I already told you about. Okay, good. What I want to point to is the following thing. I mean, just to understand how do I make this change of coordinates and how I construct this momentum space. As I already stressed, the form dispersion relation that I told you about a few minutes ago is related to the standard one, right? In this funny way. These guys on the right-hand side form the Lorentz vector with respect to the ordinary Lorentz transformation. Okay? This guy, P0 squared minus P squared, is a Lorentz scalar with respect to the Lorentz transformation. Okay? So the idea is the following. Why don't we consider a 5-dimensional coordinates in which the 4-dimensional coordinates form a Lorentz vector like this, and the 5th coordinate be a Lorentz invariant. And we know what Lorentz invariant is. Lorentz invariant is actually a function of P0 squared minus P squared. So the idea is now to start with the 5-dimensional space, build the coordinates in which 4 coordinates in this 5 dimensions are 4-dimensional Lorentz vector. The 5th coordinate is a Lorentz scalar. It reminds a little bit Kaluza-Klein program. And then find out what is the manifold, what is the manifold that coordinates k and k0 describe. And as you will see, it's going to be the submanifold of the Sitter space. I'm not sure, is it clear what I'm saying now? I changed coordinates from P and Pi to K and K0, right? There was a change of coordinates which gave me some modified dispersion relation. Now I go to 5th dimension, adding as a 5th dimension the expression for the form dispersion relation, which is a Lorentz scalar. And now I consider the map from P0, Pi, and P4. So map from coordinates P0, Pi, and P4 to the coordinates K0 and K as an equation that defines the surface. Okay, so let me do it explicitly. I added the thing, so there was the motivation. I have the coordinates P0, Pi, and P4, the coordinates in 5-dimensional Minkowski space. I know the action of boosts on this, and the Lorentz action of this. And the map is, there is a map from K0 and K into P0, Pi, and P4. So this map defines a surface, right, in 5-dimensional space, which is a non-trivial surface. Also, I know how boosts and rotations actually act on the surface. So I have the action of the Lorentz, natural action of the Lorentz on this manifold. And then the question is, what's the manifold? Well, the manifold is this one. If you take actually the square of this with a minus plus the square of this plus the square of this, you find that this is kappa squared. Well, as a matter of fact, if you open Birrell and Davis or any textbook in cosmology, you will find exactly these transformations as embedding, as a transformation or as a definition of the Sitter space as embedding in a flat space 1 dimension higher. Okay, so we know that the manifold, which is described, the momentum manifold, which is described by coordinates K0 and K, okay, is, so forget about this derivation and this argument. At the end of the day, what we're having, we have a manifold, which is defined as a surface in the 5-dimensional space, This is a four-dimensional surface with coordinates k0 and k, which is defined to be, it must be a submanifold of the zeta space, but it's kind of a special submanifold, because notice that if I add p0 to p4, then this term cancels and this term gives you just an exponent, right? So it must be positive. So this is a portion, so the manifold we are talking about is a portion of momentum of the zeta space with this condition satisfied. So this is this manifold with this condition. P mu, so P0 and Pi, is a Lorentz vector. We know it already from the construction, so it transforms as a Lorentz vector. And then P4 is a Lorentz scalar, which can serve as a dispersion relation. So now we know we need the action. We need the action. We know that we have coordinates in momentum space. We know that momentum space now is some submanifold of four-dimensional de Sitter space. That's first. Second, what we know, or the thing that we really need to do is actually to find out how to generalize this action so as to incorporate the curve geometry. Well, as we know, I should. Okay. So forget a moment about this dispersion relation, because at the end of the day we just use the dispersion relation that I talked to you about. But let me consider this. Let me consider the kinetic term. In the standard relativistic particle, the kinetic term is xa times pa. We are in a flat space. We have x dot a times pa. This is the kinetic term. Now let me try to exchange this action into the action of relativistic particle moving in curved space-time. There's an easy way to do that. Actually, usually people use the metric formulas, but it's almost trivial way to do this. It uses I don't know if you know about tetrad formulation of gravity. Tetrad is essentially square root of metric tensor, and it maps from space-time manifold in momentum with coordinate x mu to the kind of an ambient Minkowski space with coordinates labeled by the index a. Then you can, the only modification that you need to go from this dispersion, from this action for relativistic particle in a flat space, is actually to add the tetrad here. It's almost trivial. Why it's trivial? That's the only thing you can really do, because in the curved space, x carries the curved index because we have a curved manifold. P still carries the flat index because the momentum space is flat. So we just need an object that translates from flat coordinates to curved coordinates. And this object is a tetrad, as you know from general relativity. And then you can take this action, you can take equation of motion following this action, and then you find out, which the calculation is now. I really recommend everybody to make this calculation, and then you find out from this calculation that actually the resulting equation of motion are geodesic equation, the standard geodesic equation in matrix G mu. Okay, it's a little bit. I mean, this exercise is not exactly trivial, but you get it. At the end of the day, you get it. You need to assume that the connection is torsion-free, and then you get the standard geodesic equation from this action. All right, so what we know, when in transition from flat space-time to curved space-time, the only thing I need to do is actually to change this kind of a delta with a non-trivial tetrad that expresses the curved to the fact that space-time is curved. So let's try to do the same thing for momentum. Okay. For momentum, the situation is slightly more complicated because now not only you really need to change the kinetic term, but you also need to change the dispersion relation, because p squared is no longer good, k squared is no longer good at dispersion relation. But let us do one thing at a time. The first thing is that you remember we had x dot p goes into x dot mu e times p. So in order to do the same thing, the analogous thing, I need to move the dot to k. In the flat space, it doesn't really matter because the difference between x dot k and xk dot is a total derivative, which is inessential, at least if you don't care about boundary terms. But here it is essential. You really need to have a dot here, otherwise it doesn't work. So this is the kinetic term. This is exactly how it was in the curved space. I just make momentum space curved. And again, I need to have a momentum space tetrad, which is this one, to translate the curved momentum index at this time to the flat space-time index. Okay? And then I have the dispersion relation here. And as a matter of fact, this theory is manifestly invariant under Poincare symmetry, as I will show you in a moment. So, but first of all, let's find out what the tetrad is in the case of the de Sitter momentum space. Okay. So how to calculate this tetrad? I start with the 5-dimensional metric. So I have a 5-dimensional Minkowski space in which I embed my de Sitter momentum space. These are the embedding coordinates, right? This is this relation actually tells me the relation between the Minkowski 5-dimensional Minkowski coordinates and 4-dimensional de Sitter coordinates, right? What I do, I now calculate dp0, express it over with respect to as something times the dk0 plus dki and so on and so on. I substitute it here. And it turns out, surprisingly, you were saying that, well, this is a simple metric, but this looks pretty horrible, right? But then, when you do this calculation, you found that induced metric on the 4-dimensional manifold is extremely simple. There's just the Sitter metric, right? For all of you who know cosmology and inflationary model, this is just the Sitter metric, right? And flat, the flat de Sitter metric, essentially. All right, so if I have the metric, I also have a tetrad. Immediately, the metric is diagonal, right? So it's pretty trivial to find what the tetrad is. And these are the components of the tetrad. So non-trivial component of the tetrad is E00 equal 1, because here I have a coefficient 1. And there is EI alpha. It's just a square root of this guy. It's just this one. Okay, and you easily see that if you multiply this guy by eta 00 minus eta 00 E00 squared plus eta ij ei alpha ej beta, you just get exactly this metric. Okay, good. So you have the metric, you have the tetrad, and you have the action. So this is the action of a particle with curved de Sitter momentum space. It has a standard kinetic term in 0 direction, and it has modified kinetic term in the space direction. Okay, if kappa goes to infinity, this term is 1. And we just have the standard one, the standard kinetic term. And here I have this modified dispersion relation. All right, the properties. Okay, so let me, before I talk about the properties of this model, let me tell you that this model really serves as the basic model for investigation in doubly special relativity. I mean, the doubly special relativity was formulated originally as a very general theory with additional scale and stuff. So you can think you can think of many models, but this model is particularly simple and particularly rich. So most of the practical investigations are actually based on this particle or on this model. This model is not completely unique. You can start with this model, but then you can actually modify it. And there is one modification that is pretty common, useful, is that if I change the coordinates in momentum space in this way, I get this model with this Lagrangian, with this action, which is slightly different than this one, but it actually has the same physical properties, or at least as far as I know, there is no distinction. So at least this kind of transformation that doesn't change any physical properties of the model.
From the first model to the second, the k dot has been changed. The middle one. The x k dot has been changed into x dot k.
But I also changed the sign.
So you integrated again.
At this moment for this theory, I freely integrate by part and I don't bother about the boundary term. Tomorrow, it will turn out that the boundary terms actually really matter. Well, they do matter. We know that there is a lot of activities in gravity nowadays, which is concentrated really on this boundary, on the boundary terms. Anyway, what I wanted to show you is there are two models that are these are the particle models. There are simple modification of the standard relativistic particle. The modification is here, and the modified dispersion relation. Okay. But as I'm going to show you now and tomorrow too, there is a very rich structure behind it. Okay, so let me actually. This is actually pretty. I'm not going to give you the details. I just flash these transparencies. You can check it explicitly if you like, or you can find the explicit proof in the book that I mentioned at the beginning. It turns out that in terms of these k variables that I take as a fundamental variables now, that the boost transformation of the k0 component is just the standard one, but the boost transformation of the vector components of k actually modifies. It's highly nonlinear. It takes this form, pretty complicated, and then you check that this that you can make actually the Lagrangian invariant with this modified with this kind of a modified transformation of position variables. Now I'm talking the position variables, not the space-time coordinates, because the physical meaning of them is not completely clear, at least in general, basically. Okay, so these are the Lorentz transformations. The Lorentz transformations are kind of complicated. You can check that's true, but there is nothing special about, nothing particularly at this moment interesting for us. What is interesting, so what's going to be relevant and extremely relevant later on, tomorrow, are going to be this space transformation. And basically you find that which is easy to find. So let me write it for you. You remember the action was something like, the kinetic term was something like say x0 k dot 0 plus, if I remember correctly, it was e to the minus k 0 over kappa xi k I dot, right? So obviously, delta x0 being epsilon 0 is a transformation, and of course k do not change under boosts under translations. Momenta don't change under translations, right? It's physically clear. Even if I have a particle, right, I translate it, its momentum is the same, right? Nothing changes. So the momenta don't change. And indeed, if I translate x0 by a constant epsilon and don't move xi, then of course, then this is a total derivative. And as I said, I don't bother about boundary terms at this moment. And in order to make this guy invariant, I need to first kill this guy. Notice that I need to have a transformation as well. This is an important point. The field equations in a moment that I will show you in a moment will force k to be zero, k to be time invariant, time independent. But the transformations must be a transformation of the action of check. So in order to make it invariant, I need to first multiply this x, right, by this factor to kill it, and then multiply it by a constant. So obviously, this is the right transformation. Okay? You see that if I have delta x is epsilon y times e to the minus k0 over kappa, this, sorry, that's plus here. Is it plus or was it minus? I'm confused. For a moment, let me check. Perhaps I made a mistake. No, it's plus in action. So I made a mistake here. So this is how the action looks like. I first multiply by the factor e to the minus k0 over kappa. This cancels, and just take a constant, and it becomes a total derivative. Good. And this translation, so remember this, please remember this, because that's going to be this translation invariant is going to be a central point for what I'm going to say tomorrow, and also for some tutorial that I would like to that I would like you to say, some exercise that I would like to do for you with you next time. So this is the action. These are the transformations. Just let me go on. Equations of motion. All right, equations of motion are, well, okay, the first equation is the equation of motion for k is just a trivial one. If you look at this action, which is here, if I vary over k, over x, I just get that k0 is 0, k dot 0 is 0, k dot I is 0, so that's nothing surprising. There is a little bit, so I rewrote a little bit the equation for k in a kind of a simple form, which is convenient again to compute the velocity. Okay, it's convenient for computation of velocity. This is the and perhaps if I have time, I will actually. We'll talk more about it during the tutorials. This is another exercise I would like to make with you. This action, which actually the animation is not in the right order, but doesn't matter. Speed of light. Well, you would think, well, now it turns out that to compute the speed of light in this theory is not that trivial, right? Because you have a complicated dispersion relation, and these equations of motion are pretty complicated. But at the end of the day, you find that this is actually one. And this is the exercise that if I have time, I'm going to work out it with you in details tomorrow during tutorials. Okay, it's pretty relevant, it's pretty important, because it says that if you believe that DSR, this particular class of DSR models, then the physical prediction of this DSR model is that the velocity of light is independent. The velocity of light is just one in this theory. The theory is deformed in a non-trivial way, but the velocity of light is still equal 1, which means that if I It would naively mean that if I observe the distant source, I would observe, so this is a phenomenological prediction. I observe the distant source, all the photons independently of energy should actually arrive at the same time. Okay, that's a phenomenological prediction, important. And well, okay, that's what it is. However, as you will see tomorrow, there is a twist to it. And at the end of the day, this theory is actually described non-trivial dependence of the time lag between the high energy and low energy photons, arrival time. But the mechanism is much more complicated than just this. I mean, the velocity of light for any observer is just 1. However, due to some non-trivial mechanism related to something called relative locality, actually the arrival time of photons of different energies emitted at the same time might be different. Okay, good. So let me continue. How much time do I have? I still have 10 minutes. Well, so let me skip the symplectic structure. I will just you will have. I believe that you will have an access to this notes. I will not dwell on this. Oh, sorry. This I need. You can compute the Poisson brackets from this Lagrangian. You can compute the Poisson bracket, and the important fact, the important thing you really, which is of course in red because it's important, but it's completely invisible because it's in red. So if you compute the Poisson brackets, you find the following structure. This is important. You find that the Poisson bracket of time and space is not zero. Space-time becomes non-commutative. This model predicts non-commutative space-time. Right? This is important. This is big. And the space-time of this sort with this type of non-commutativity is called Kappa-Minkowski. As you could easily imagine, there is no real other name that you can use here. That's Kappa-Minkowski space. Kappa and Minkowski, right? So we have a flat space. So the space-time of this model is a flat space, but non-commutative. And non-commutative in a non-trivial, in extremely non-trivial and extremely nice way. So let me explain why it is non-trivial and nice. So instead of having Poisson bracket, let me actually take a commutators. Well, imagine that you quantize the model, and you have instead of a Poisson bracket of a particle, you just have a quantum mechanical commutator of these guys, xi, which is, you shouldn't think literally in this way. So these are not the operators corresponding to the space-time positions, but they're just some operators. So I quantize this algebra, I get such an algebra. And in quantum theory, you know what you do. In quantum theory, you find essentially the whole quantum theory is about representation theory. So you take some algebra of operators, and then you look for representations, and you analyze the representations. And the simplest representation of this algebra, the simplest matrix representation of this algebra is actually 5 by 5, surprisingly, but not that much, right? Because you remember that we had this momentum space embedded in the 5-dimensional space. And then it turns out that this algebra, this non-commutative algebra of positions, is actually represented nicely by 5 by 5 matrices, or the linear operators in 5-dimensional space. Cool, good. So, but then now, if you know algebra, you know that if you have the commutator algebra of this form, it forms what is the general name of the structures like this, in which you have a commutator of 2 elements and you get linearly another element on the right-hand side. So what is the structure? This is Lie algebra. Nice. If I have a Lie algebra, I know I have a Lie group. So let's see what the Lie group is. And especially, let's see what's the manifold of the Lie group is. Okay, good. So let me compute this. And before I compute it, let me actually have a digression. The digression is so important that I even may not be able to finish on time. But okay, digression is, and I should have actually moved it into the very beginning. This is a beautiful citation from Gauss, who essentially claimed that he's not happy about Euclidean geometry because if geometry of the world wasn't Euclidean, then it would require scale, right? If you have a curvature, if you have a geometry, constant curvature geometry, it essentially has a curvature scale. So what Gauss was complaining about, he was one of the founder of non-Euclidean geometry. He was complaining that, you know, the word geometry is Euclidean, but it would be so nice if it wasn't, because then we would have a scale and we would play so many nice things in mathematics. But at the time, it was beginning of 19th century, everybody believed it is completely natural that this physical space is Euclidean. So he was really complaining about the Euclidean, that the space is Euclidean. So if you turn this argument around, you may say that if there is a scale, you may expect a non-trivial geometry. Or let me take it into just a statement or the motto, which is that everything is curved unless it cannot be. Well, the Euclidean space cannot be curved because there is no scale. But if you have a scale, it can be curved and it starts being really interesting. All right, so now let me go to this. Let me actually give you the scale and geometry and example. So let me come back to special relativity. I told you that in Galilean relativity, there is no real alternative to the linear composition of velocities, right? That I told you at the very beginning, because there is no scale. But if there is a scale, there are lots of non-trivial structure may arise. And actually, if you compute what is the composition of velocities in special relativity, this is non-trivial calculation actually. So there are 3 velocities and I would like to compose them. Okay, so I have a particle moving with the velocity v with respect to me, and there is another observer which moves with velocity u with respect to me. What is velocity of the particle with respect to the second observer? Well, this is highly non-trivial if the velocities are not collinear, and the result is here. You see that this expression is very complicated. As a matter of fact, you may check that this is not symmetric. Well, it's obviously not symmetric, but you can also check that it's even not associative. And this, of course, has its physical counterpart, which is the theory of Thomas precession. Theory of Thomas precession is essentially a theory about this non-associativity of the composition of 3 velocities in special relativity. So we see that there is, and this is extremely rich. I mean, geometrically, this composition is extremely rich. It contains a lot of interesting features. So people wrote books about it. All right. So that was my point. And now let me actually construct this group element and then I finish. I will probably be, 5-10 minutes. Take 5 or 10 minutes of the break. So I have this xi and x0 are these generators in Lie algebra languages, in the Lie algebra language, and then I can form the group, just the group element, which because xi commute, I can actually form e to the xi ki xi, e to the I xi ki. This is a natural object, and then I multiply it by this object. This is just a convention. You can do it other way. Another way. You can actually take e to the I ki xi plus I k0 x0. That would be that would be result in different coordinates in momentum space, which are relevant again. I will mention that tomorrow. Anyway, You compute this matrix. You can compute it. It's easy because the group in question is called AN3 group, which A denotes abelian and N denotes nilpotent. So the matrices, you can check that the matrices representing Xi are nilpotent matrices, meaning that X cubed is actually 0. Xi cubed is actually 0 as a matrix. So it's actually pretty easy to compute this object, and the result is this. And look at this particular column. And this column is something that we know already. Right? These are our coordinates on momentum space, on the city momentum space. This is exactly what it was. So now, this is the group element, but then I want to get a description of a group manifold. So what is the group manifold? Well, the group manifold is if group acts not freely. What is the name that the group acts that it actually moves, that it gets into all group elements just by action on one? Sorry? Yeah, I guess so, yes. Yeah, thanks. So the group acts transitively. I am not completely sure, but I think you're right. But I explained already the notion. The group acts transitively, which means that I pick up one element and act with all possible group elements on this element. I get the whole group manifold, right? Yes, that means that the transitivity, if I remember correctly, the definition is mathematically that the orbit of any point in the group is just the whole group, right? That's the definition. I'm not sure that it's called transitivity, but I believe you're right. But the definition is that in terms of orbit, the orbit of or acting on a point on any element of the group is the whole group. Right. So let's use this fact. And I take this particular point, which is the simplest one I can think of, which is 0, 0, 0. So the point is Lorentz invariant, right? Because you remember the Lorentz subgroup actually acts on these 4 first entries. So if I take it 0, 0, 0, it's Lorentz invariant. I want this origin to be Lorentz invariant. Physically speaking, this origin is essentially a point of 0 energy and 0 linear momentum. Right? It's a nice point, very special point in the momentum space. It has this coordinate kappa. Kappa is the scale. Well, I need to have the scale, right? That there is this point is on a particular distance from the origin, and then I act with this group with this matrix of the group that I computed before, that I showed you before, and I found that in the coordinates, in this coordinate P0, P4, and Pi, we have the point in the group here, so the point on the group manifold here, or the manifold which is isomorphic to the group manifold, strictly speaking, is actually characterized by these 4 numbers, K0, Ki, and from embedding point of view, this looks like this. So this is again as we had before, just a submanifold of the zeta space. All right, this is the figure. And that's the end. We actually got to the summary. Good. And I'm almost perfectly on time. Good. So let me summarize. I will start tomorrow with the summary, but let me do it today. Well, so doubly special relativity is to replace special relativity as a theory that incorporates some quantum gravity phenomena in some particular limit. So it should carry some information about some traces of quantum gravity that might be phenomenologically relevant. This theory is characterized by 2 scales of velocity and of mass with deformed Poincare invariance. They're deformed in the sense that the Lorentz transformation and translation and stuff contains these kappa parameters, so they are not just the standard one. In the class of phenomenologically, so phenomenological information in the class of models of DSR, the speed of light, misspelling, is momentum independent. That's something that we computed. The mass scale can be incorporated, and this is actually very nice and beautiful, and I really love this result. The mass scale can be incorporated geometrically by identifying it with the curvature of momentum space. So, and I think, you know, for me, because I am by training the relativist, general relativist, for me, if I can see something geometrically, it's always easy to understand and beautiful. So that's why I really love this result. So that's it for today. Tomorrow, hoping that we're gonna proceed in the same pace, we'll talk about relative locality. And then, and then on tutorials, I would like to do two things. First thing would be to find the velocity of light with the relative locality effect, or the time difference between two rays of different energy. And what else? I told you that was something we wanted to, well, was it what? Oh yeah, we wanted to find out that the velocity of light in this deformed theory, DSR is just one, because it's going to be important. That's important for the for the lectures. I would like to show it explicitly, and if on tutorials we'll still have some time left, we'll do some little computations. Okay, thank you.
I had a question about when we come to the point where we define the deformity ASB, like, okay, I have four mass shell, which was why we just simply recycle the whole of the estimations of the coordinate. So my mother doing the momentum coordinate and not just doing that we had.
Yeah, right. Okay. Well, so let me clarify. That was not really important a statement. It was kind of a line of argument, really. So the starting point was that I can modify the special relation and get a non-trivial theory which is Lorentz invariant violating, right? And this is a class of theories that people consider for many reasons, or used to consider and discuss. Both thinking about the field theoretical aspects and phenomenological aspects. Okay, so this is Lorentz invariant violating theory, and now the question is, can we do any better than that? So, well, better probably it's a wrong word. Can we do differently? Can we actually have modified the special relation and at the same time having the all the symmetries preserved on the particle level? And this is part of this argument about changing coordinates was actually part of the reasoning, which points out into actually the constructing. So at the end of this, the argument was that it might be interesting actually to consider a theory with non-trivial curved momentum space as a fundamental theory, and which the momentum space is curved in such a way so as to preserve manifestly or explicitly the Poincare invariance in the modified form. All right, so that was only the argument. I'm not saying in Lorentz invariant violating theories, you stick to one coordinates in momentum space. That's it. Okay, there is one momenta, no question about it. But if you try to go in different direction, so as thinking that relativity principle is so fundamental you cannot really abandon it, then the simplest way to handle this is just to have a non-trivial geometry of momentum space. Okay, does it clarify? Right. Okay. Good. Very good point. Yes, that's true. That's true. Sure. Right. Uh, that's a very good point, because the point is that the point is that I can change coordinates, right? And I can change freely coordinates. So if I can change free coordinates, why to change it all, right? That's your point, basically. Of course, it's a very good point. And so the question is how to construct the theory in such a way that you cannot really go back. If you have a curved momentum space, right? The curvature is a scale. I mean, it's there. It must be visible. So if I change coordinates, like in GR, basically I can change coordinates in flat space-time, but physics doesn't change, apart, of course, from the global issues. But locally, I change coordinates, nothing changes, right? This is just GR. So if I stick to the flat momentum space and I change coordinate, nothing changes, of course. But if I already have an untrivial geometry, I cannot really, if kappa is finite, right? I cannot really make a curved geometry flat. So somehow I must be able to see the effect of this curvature one way or another. I mean, in this class of model, you cannot see the effect of the curvature just measuring the speed of a massless particle. This effect is not there. But I will try to argue next time, tomorrow, there's gonna be an effect if you start considering the multi-particle states. Okay, so the single particle is essentially trivial, but if you start considering the many particles, it starts being non-trivial, and then there is no way to undo the curvature. Okay. Yeah, right. I mean, a sphere and the flat space locally look exactly the same, and the particle essentially just measures just the local structure. Okay, so that's why it might be non-visible, right? You can always choose locally, on sphere the flat coordinates, but sphere is a sphere, so there must be effects that actually see the curvature of the sphere. Right? And these effects cannot be really local. They might be, you can really move a little bit from the origin or from some point. So compare, well, think how you can measure a curvature of a sphere, right? You cannot measure the curvature just having one point. You really need to move a little bit compared to things at different points. And this is something geometrically that's gonna show up tomorrow.
Perhaps we can connect with the and to talk about it.
Right. So I think that perhaps if you have still some questions and you think they're interesting to all of the audience, why don't we spend some time on tutorials tomorrow, just as asking and answering the question, especially. This is going to be after the second lecture, so I think some things are going to be